Non-aqueous solvents. A solvent is generally defined as a liquid which has the ability to dissolve other substances. Water is considered to be a universal solvent since ancient times. Majority of the reactions are also carried out in water because of its easy availability and unique physical and chemical properties. There are solvents other than water that can be used to carry out chemical reactions. Solvents other than water are called non-aqueous solvents. Before we discuss the chemistry of non-aqueous solvents, it is appropriate to understand the important role of a solvent plays in the chemical reaction. Role of solvent in a chemical reaction. A solvent has two important roles in a chemical reaction. The first and the most important role is to bring the reacting substances close to each other in a finally divided state. If the reactants are not intimately mixed, the rate of the reaction will be very slow. For example, the reaction between barium chloride and silver nitrate in the solid state will proceed very slow. However, in aqueous solution, the reaction proceeds very rapidly. Thus, the role of solvent is to accelerate the rate of the reaction. In addition, it is possible for a solvent to change the course of the reaction. In water, barium chloride and silver nitrate react with the twinkling of an eye to form white precipitate of silver chloride. The same reaction in liquid ammonia is completely reversed. A solvent also affects the rate of the given reaction. For example, the reaction between iodoethane and triethylamine occurs to form tetraethyl ammonium iodide at a reasonable speed in hexane. If the above reaction is carried out in benzene, the rate of the reaction becomes 80 times that of hexane. In acetone, the rate of the reaction is 500 times, where in nitrobenzene, the rate of the reaction is 280 times. We can see that the rate of above reaction in various solvents proceed in the order nitrobenzene much more than acetone, much more than benzene and more than hexane. Another important role of the solvent is to allow rapid separation and purification of the products. The precipitation of the chlorides in the above reactions allows for an easy separation of the products. We should recall that silver chloride is insoluble in water, whereas barium chloride is insoluble in liquid ammonia. Suppose you are asked to prepare an anhydrous sample of copper sulfate. How will you prepare it? Definitely, you cannot use water as solvent. This means we need another solvent. Anhydrous copper sulfate can be cleanly and conveniently prepared in the molten solvent mercury bromide according as CuBr2 plus HgSO4 in the presence of HgBr2 liquid gives HgBr2 plus CuSO4. Physical properties of solvents. The selection of the solvent in a reaction is generally made with regard to some specific properties that may help to carry out this reaction by effectively dispersing the reactants and separating the products more conveniently. Some of the important physical properties of the solvents are discussed below. First, melting and boiling point. Majority of the chemical reactions are carried out in the liquid phase. As a result, the liquid range determines the usefulness of a particular solvent. Melting and boiling point of several solvents are given. An inspection of this table reveals that water has an excellent liquid range from 0 to 100 degrees Celsius. As a result, it is an ideal solvent for carrying out chemical reactions in solution at room temperature and atmospheric pressure. Both liquid ammonia and liquid sulfur dioxide are ideal solvents for carrying out reactions at low temperature. Second, dielectric constant. Dielectric constant measures the polar nature of the solvent. This property is used to evaluate the solubility of polar or non-polar compounds in a solvent. According to Coulomb's law, the forces between two charged particles is given by the expression F is equal to even into E2 upon dr square, where E1 and E2 are the charges on the two particles, R is equal to internuclear distance between the particles, and D is equal to dielectric constant of the solvent. A high value of dielectric constant indicates that the force of attraction F between the charged particles is less, and hence a small amount of energy is required to separate the ions. It means that it is easy to dissolve an ionic solute in a solvent of high dielectric constant. In other words, dielectric constant determines the ability of a solvent to dissolve ionic compounds. The solvents with high dielectric constant should be able to dissolve ionic and polar compounds. A solvent is considered to have high dielectric constant if the value lies between 50 to 80. A medium dielectric constant if the value lies between 20 to 50. And the low dielectric constant if the value lies between 2 to 20. Thus, solvents like liquid ammonia and liquid sulfur dioxide with low dielectric constant should show decreased ability to dissolve ionic compounds, especially the multi-charged ions. As a result, carbonates, sulfates, and phosphates are less soluble in solvents with low dielectric constant. The dielectric constant and polarity of the solvent are related with one another. Third, heat of fusion and vaporization. Heat of fusion is defined as the amount of heat absorbed by 1 mole of the substance to change from solid to liquid state. Similarly, the amount of heat absorbed by 1 mole of the substance to change from liquid to gaseous state is called the molar heat of vaporization. The magnitude of heat of fusion and vaporization gives us some insight into the nature and strength of forces holding the molecules in the solid or the liquid state. A high heat of vaporization suggests that the intermolecular forces operating in the liquid state are strong and vice versa. Therefore, the heat of fusion and particularly the heat of vaporization are significant in evaluating the usefulness of the solvent. The ratio of the heat of vaporization to the boiling point on the absolute scale is a constant called Troughton constant, and it has a value around 21.5 for normal liquids. Normal liquids are characterized by single molecules without any bond between them. A value higher than 21.5 suggests association of molecules of the liquid to form larger aggregates. Such liquids are called abnormal liquids, which include ammonia, water, hydrogen fluoride, and sulfur dioxide. We have already learned that molecules of liquids which undergo association are polar. Polarity in a molecule arises when the electron pair forming the bond is shared unequally between the two bonded atoms. Association between polar molecules arises from the tendency of polar molecules to orient themselves so that the positive end of the molecules are near the negative end of the adjoining molecule. In addition, the polar molecules surround the positively charged cations in a way that the partially negative ends of the polar molecules are oriented towards the cation. Similarly, the polar molecules surround the negatively charged ions in a way that the partially positive end of the polar molecules are oriented towards the anion. Water, being a polar molecule, orients its negative ends towards the cation, forming the first shell of water molecules around the cation. A careful The heat of fusion of water and ammonia are nearly similar. It implies that the forces which hold the molecules together in water and ammonia are nearly of the same magnitude. The heat of fusion in case of sulfur dioxide is relatively high compared with that of hydrogen fluoride, suggesting that forces holding hydrogen fluoride molecules are weaker. Fourth, viscosity. It is an important property of solvents. Viscosity measures the difference in the rate of flow of liquids. Water, liquid ammonia, and lower alcohols flow rapidly under gravitational force and have low viscosity, whereas high molecular weight hydrocarbons, anhydrous sulfuric acid are highly viscous and flow at much lower rate. Viscous liquids lower the mobility of ions and thus reduce the electrical conductance of solutions of the electrolytes. Experimental difficulties with viscous solvents are observed in precipitation, crystallization, and filtration processes. Fifth, self-ionization. The acidic and basic nature of the solute dissolved in a solvent depends upon the self-ionization of the solvent. Any solution that by direct ionization or interaction with the solvent gives the cationic characteristic of the solvent resulting from self-ionization of the solvent is called an acid. Similarly, a base is any substance that gives the anionic characteristic of the solvent. Types of solvent. Non-aqueous solvents can be broadly classified into four types: a protonic and non-protonic solvent, acidic and basic solvent, ionizing and non-ionizing solvent, coordinating and non-coordinating solvents. The above classification is based primarily on the chemical properties of the solvents and are discussed below. Protonic and non-protonic solvents. Protonic or protic solvents are those from which hydrogen ions or proton can be abstracted. Some of the commonly available protonic solvents are H2O, HF, HCN, and H2SO4. Non-protonic or aprotic solvents are those from which hydrogen ions H positive cannot be abstracted easily. Frequently encountered examples of such solvents are CHCl3, C6H12, liquid SO2, etc. Acidic and basic solvents. Solvents which are capable of donating hydrogen ions H positive are called acidic solvents, whereas solvents which are capable of accepting hydrogen ions are called basic solvents. Examples of acidic and basic solvents are acidic solvent HF, H2SO4, CH3COOH, etc. Basic solvents NH3, pyridine, hydrazine, etc. Ionizing and non-ionizing solvents. There are several solvents which undergo auto-ionization or self-ionization to different extents. Such solvents are called ionizing solvents. Frequently encountered examples of ionizing solvents are given. There is another class of solvents which are non-polar and do not ionize at all. Such solvents are named as non-ionizing solvents. Examples are benzene, hexane, tetrachloromethane, etc. Coordinating and non-coordinating solvents. There are several solvents which are capable of coordinating with the ions of a solute. Such solvents are designated as coordinating solvents. Commonly used coordinating solvents are ammonia, dimethyl sulfoxide, acetonitrile, nitromethane. On the other hand, solvents which are not capable of coordinating with the ions of a solute are called non-coordinating solvents. For example, benzene, hexane, and tetrachloromethane are non-coordinating solvents. Liquid ammonia as a non-aqueous solvent. Liquid ammonia is one of the most thoroughly studied non-aqueous solvent due to its availability and water-like properties. These days, liquid ammonia is used very frequently as a solvent for many types of organic and inorganic synthesis. Ammonia is an associated solvent through hydrogen bonding, although the extent of hydrogen bonding is far less compared to that in water. As a result, the melting and boiling points of liquid ammonia are lower than those of water. The corresponding values of water are also listed in the table for comparison. The dielectric constant of ammonia is smaller than that of water. As a result, liquid ammonia is much better solvent for organic compounds than is water. On the other hand, liquid ammonia is a poorer solvent for ionic compounds than is water. There are, however, a number of ionic compounds which have a higher degree of solubility in liquid ammonia. The solubility of some common inorganic compounds in liquid ammonia. Ammonium salts, regardless of the anion, are highly soluble in, in liquid ammonia. Inorganic compounds with highly polarizable anions, iodide, thiocyanates, are more soluble than the non-polarizable anions, fluoride, chloride. Solubility of halides decreases from iodides to chlorides. It is noted that highly charged ions with high charge density like fluorides, hydroxides, oxides, sulfates, carbonates are soluble in liquid ammonia. Autoionization of liquid ammonia. Liquid ammonia undergoes autoionization in a manner similar to water. However, the extent of autoionization is smaller than that of water. The ionic product of ammonia at minus 50 degrees Celsius is 1.9 into 10 raised to the power minus 33, which is very low compared to that of water, which is 1 into 10 raised to the power minus 14 at 20 degrees Celsius. Chemical reactions in liquid ammonia. Chemical reactions occurring in liquid ammonia are similar to reactions occurring in aqueous solution because liquid ammonia is similar to water as a solvent. Some of the important reactions that take place in liquid ammonia are given below. First, acid-base reaction. The autoionization of ammonia gives ammonium ion and amide ion. According to solvent system concept of acid and bases, any substance that by direct ionization or by interaction with the solvent gives the cationic characteristic of the solvent resulting from the autoionization of the solvent behaves as an acid in the solvent. Similarly, a base is any substance that gives the anionic characteristic of the solvent. Thus, NH4Cl would behave as an acid, whereas KNH2 would behave as a base in liquid ammonia. Therefore, the neutralization reaction would be acid plus base gives salt plus solvent. That is NH4Cl plus KNH2 gives KCl plus 2NH3. Acids and bases in liquid ammonia are called amino acid and amino bases respectively. Thus, amino acids are substances which in liquid ammonia furnishes NH4 positive ions, whereas amino bases are substances which in liquid ammonia furnishes NH2 negative ions. Solutions of metals in liquid ammonia. A unique feature of liquid ammonia as a solvent is its power to dissolve the alkali metals and to lesser extent the alkaline earth metals and aluminum. The metals dissolve to impart blue color. The blue colored solution is independent of the metal dissolved and has a broad maxima around 15,000 Armstrong. The solutions are extremely good conductors of electricity. As the concentration of the metal is increased, the solution becomes bronze colored. The dilute solutions are paramagnetic, but the paramagnetic behavior decreases with the increase in concentration of the metal. Highly concentrated solutions have conductivities nearly as high as pure metals. The equivalent conductivities of lithium, sodium, and potassium are given. It is believed that the blue color of the solution is due to the presence of alkali metal ions and free electrons in liquid ammonia. In dilute solution, the metal ion and the electrons are ammoniated as solutions of alkali metals in liquid ammonia are metastable. A small amount of impurity is sufficient to catalyze the formation of amide. A rusted nail will be capable of serving as a catalyst for the formation of sodium amide. However, if both alkali metal and ammonia are extra pure, the alkali metal dissolved in liquid ammonia can be kept for many weeks at low temperature, and one can recover the alkali metals on evaporation of the solvent. However, when alkaline earth metals dissolved in liquid ammonia are evaporated, the free metals are obtained. Instead, ammoniates of the type M of NH3 6 are obtained where M is the alkaline earth metal. Reactions of amino acids. Amino acid is a substance which in liquid ammonia supplies NH4 positive ions. Thus, all ammonium salts, irrespective of the anion, are amino acids in liquid ammonia. These acids undergo a number of acid-base reactions given below. First, the amino acids react with the reactive metals, alkali, alkaline, and other metals, and liberate hydrogen gas. Second, ammonium salts dissolved in liquid ammonia are used for the synthesis of various hydrides. For example, reactions of magnesium silicide and magnesium germide with ammonium solution of ammonium bromide give high yields of silanes and germanes respectively. Third, amino acids undergo proteolysis in liquid ammonia. A number of compounds like urea, acetamide, sulfonamide, sulfamic acid that do not donate proton to water readily donate proton to NH3 in liquid ammonia. Thus, these compounds act as amino acid in liquid ammonia. Sulfamic acid behaves as a dibasic acid in liquid ammonia whereas in water it acts as a monobasic acid. This is because NH2 group is not acidic enough to donate to water. Reactions of ammono bases. The most common reactions in liquid ammonia involving ammono bases are reactions of the amide ion NH2 negative. Most commonly used ammono base in liquid ammonia is potassium amide KNH2 because of its high solubility in liquid ammonia. The solubility of lithium amide and sodium amide is very small in liquid ammonia. Reactions of such solutions with metal ions in liquid ammonia are used for the preparation of the metal imide, and metal nitrides. Care should be taken in handling the imide and nitrides of lead, thallium, or bismuth respectively, as these detonate with explosion. Salts of these amino acids can be readily prepared by their reaction with a very strong base in liquid ammonia. Example, sodium uracil can be prepared by combining urea with sodium amide in liquid ammonia. It is important to note that sodium uride cannot be prepared in water. Similarly, aluminum salts combine with potassium amide and liquid ammonia to form soluble amide complexes as shown below. Redox reactions. Oxidation reduction reactions are well known in liquid ammonia, wherein the nitrogen and hydrogen of ammonia undergoes a change in the oxidation state. Redox reactions are classified in three classes, which are discussed below. First, redox reaction where alkali and alkaline earth acts as reducing agent in ammonia. Alkali and alkaline earth metals dissolved in liquid ammonia are strong reducing reagents. These blue-colored metal ammonia solutions undergo a variety of reactions in which the alkali metal gets oxidized while the other reactant gets reduced. Second, redox reactions where liquid ammonia acts as a reducing agent. A number of reactions are known where liquid ammonia itself acts as a reducing agent. For example, catalytic oxidation of ammonia in the presence of platinum, reduction of metal oxides, oxidation of reactive metals, reduction of nonmetals. Redox reaction where liquid ammonia acts as a solvent. A number of redox reactions are known wherein liquid ammonia simply acts as a solvent. Oxidizing action of various oxidizing agents is weaker in liquid ammonia than in aqueous solutions. Nitric acid is a very strong oxidizing agent in water but does not act as an oxidizing agent in ammonia. Similarly, potassium permanganate is a strong oxidizing agent in water but behaves as a weak oxidizing agent in liquid ammonia. Potassium permanganate first reduces to potassium manganate and finally to magnesium oxide by a solution of potassium and liquid ammonia. Iodine acts as a weak oxidizing agent in liquid ammonia. Solvolysis or ammonolysis. A solvolytic reaction is defined as a reaction in which the solvent molecule reacts with the solute, splitting into two parts, one or both of which may become attached to the solute molecules. In most cases, the solvolytic process results in an increase in the concentration of either the anion or the cation, which is characteristic of the autoionization of the solvent. Nearly all covalent inorganic halides, when dissolved in liquid ammonia, undergo ammonolysis. A familiar example would be the ammonolysis of bone trichloride. This reaction would continue until BNH2 whole thrice is formed. Similarly, the ammonolysis of titanium tetrachloride takes place in steps as follows. Other important examples of ammonolysis are alkali metal hydrides and oxides are known to undergo ammonolysis reactions. Ammonolysis reactions with several organic substances have been estimated in detail. In ammonolysis, the atom or ion from the compound undergoing ammonolysis is replaced by NH2 or NH or N group. Thus, organic halides which undergo slow ammonolysis at the boiling point of liquid ammonia provides a mixture of primary, secondary, and tertiary amines. Organic iodides have been found to undergo ammonolysis readily than the bromides and chlorides. Solvate ammoniates formation. When a solute is dissolved in a solvent and the excess of solvent is removed, the solid product obtained in most cases contains a number of molecules of the solvent attached to a solute by a chemical bond. Such a process is called solvation, and in case the solvent is ammonia, it is called ammoniation. The bonding that is involved in ammoniates may be explained in terms of coordinate covalent hydrogen bonding or non-dipole moment. Complex formation reactions. A number of complex formation reactions in liquid ammonia have been investigated which are similar to the complex formation reactions occurring in water. For example, zinc is precipitated as zinc amide in liquid ammonia which gets dissolved in excess of amide to form soluble aminozincate complex. Precipitation reaction. The formation of a precipitate when solutions of two compounds are mixed is one of the most common and familiar chemical reactions. These reactions are dependent upon the solubilities of the possible products in a particular solvent. As a result, precipitation reactions are highly dependent upon the solvent employed. On mixing solution of barium chloride and silver nitrate in water, there is immediate precipitation of silver chloride. The reaction proceeds in the forward reaction because silver chloride is practically insoluble in water. However, in liquid ammonia, the direction of the reaction is reversed. It means that on mixing solutions of silver chloride and barium nitrate in liquid ammonia, it is barium chloride that is precipitated. The reaction proceeds in the forward reaction because barium chloride is practically insoluble in liquid ammonia. Similarly, metal bromides and iodides are precipitated when metal nitrates and ammonium halides are mixed together in liquid ammonia. Ammonium sulfide in liquid ammonia is used in precipitating many metal sulfides from metal nitrates solution. Barium ethoxide in liquid ammonia can be precipitated out by combining potassium ethoxide with barium nitrate as given below. Similarly, sodium carbamate can be precipitated in liquid ammonia by combining ammonium carbamate with sodium nitrate in liquid ammonia. Many insoluble halides can be precipitated as complex amines in liquid ammonia as advantages of liquid ammonia as a solvent. Following are the advantages of using liquid ammonia as a solvent. Alkali metals dissolve cleanly in liquid ammonia without any chemical reaction. Alkali metal solutions in liquid ammonia are stronger reducing agent than hydrogen. The tendency of liquid ammonia to undergo solvolysis reactions is smaller in comparison to water. The solubility of ammonium salts in liquid ammonia finds extensive use in precipitating metal halides, sulfides, and sulfates. Disadvantages of liquid ammonia as a solvent. Liquid ammonia as a solvent has the following disadvantages. Ammonia has a lower boiling point, that is negative 33.35 degrees Celsius, and consequently has a smaller liquid range, only 44.4 degrees Celsius at atmospheric pressure. The reactions in liquid ammonia can therefore be carried out only at low temperature and high pressure. Specially designed apertures and equipment is needed to carry out reactions in liquid ammonia. Liquid ammonia is hygroscopic and therefore utmost precautions are needed to exclude moisture from the reaction vessel. It has unpleasant smell. Sulfuric acid as a non-aqueous solvent. Sulfuric acid is the most extensively studied of all the strongly acidic solvents. It is a good solvent for a variety of organic compounds. Most of the organic compounds accept proton in sulfuric acid and act as bases in it. Before we discuss the chemistry of sulfuric acid, it is appropriate to learn some of the physical constants of sulfuric acid. Pure sulfuric acid 100% has a freezing point of 10.371 degrees Celsius. It can be prepared by adding aqueous sulfuric acid or to fuming sulfuric acid, that is anhydrous sulfuric acid containing excess sulfur trioxide, until a freezing point of 10.371 degrees Celsius is obtained. Fuming sulfuric acid is also called oleum, that is H2SO7. The freezing point diagram for H2O SO3 system in the neighborhood of 100% H2SO4. A careful inspection reveals that sulfuric acid is a highly viscous solvent, suggesting the highly associated nature of the solvent through hydrogen bonding. As a result of strong hydrogen bonding, its high boiling point is also justified. The high specific conductance of 100% sulfuric acid indicates that the solvent autoionizes to a considerable extent. We have already learned the autoionization of water and ammonia according to the following reaction equation. The autoionization of sulfuric acid can be expressed as the ionic product constant for sulfuric acid is given by K is equal to 2.4 into 10 raised to the power minus 4 at 25 degrees Celsius. In addition to the autoionization or autoprotolysis, there are other important dissociation equilibria in case of 100% sulfuric acid. Among the most important of these is the self-dissociation reaction. Since water behaves as a base in sulfuric acid and disulfuric acid acts as an acid in sulfuric acid, we must consider two more equilibria according as the first of the equilibria proceeds extensively to the right, whereas the second proceeds to the right to a small extent. From the four equilibria mentioned above, an additional equilibria can be derived. This derived equilibria is called the ionic self-dehydration reaction. The values of the equilibrium constant of the above equilibria are the total molar concentration of species other than H2SO4, example HSO4 negative, H3SO4 positive, H3O positive, HH2O7 negative, H2S2O7, and H2O is 0.424 molar at 25 degrees Celsius. Acid-base reactions in sulfuric acid. Autoionization of sulfuric acid results in the formation of hydrogen sulfate ion and sulfuric acidium ion. Accordingly, the strongest base that can exist in 100% sulfuric acid is the hydrogen sulfate ion. Thus, strong bases in the system are solutes which yield high concentration of this ion in sulfuric acid solution. Alkali and some other metal hydrogen sulfates are strong bases similar to metal hydroxides in the aqueous system. Acids. Sulfuric acid is a very strong acid and almost all chemical species which react with it forms the hydrogen sulfate ion. Thus, a majority of substances behaves as bases in it. Because of the strong tendency of H2SO4 molecule to donate protons, molecules exhibiting basic tendencies are all leveled to the strength of HSO4 negative ion. As already discussed, majority of the substances that behaves as acids in aqueous solution do not show acidic properties in sulfuric acid. Rather, these behave as bases. For example, acetic acid, phosphoric acid, nitric acid, hydrogen fluoride, etc. all behave as bases in sulfuric acid. Even perchloric acid, which is one of the strongest non-mineral acids, is only slightly ionized in sulfuric acid and behaves as a weak acid. One of the few substances that behaves as an acid in sulfuric acid is disulfuric acid. It is formed from sulfur trioxide and sulfuric acid. The only strong acid in sulfuric acid is tetrakis, that is hydrogen sulfate, borate, that is HbHSO4 whole 4. The compound has not been prepared and isolated in the pure form, but solutions of these acids can be prepared in sulfuric acid as addition of sulfur trioxide to the above solution removes the hydronium ions as both tin and lead tetraacetate dissolve in sulfuric acid to give strong acids. There is a small number of substances which behaves as acids in sulfuric acid. Since the anions of normal salts of most of the inorganic acids are actually strong bases, then is the hydrogen sulfate ion. Such salts undergo complete solvolysis in sulfuric acid to yield hydrogen sulfate solutions. A large number of covalent compounds, both organic and inorganic, undergo proteolysis in 100% sulfuric acid, giving hydrogen sulfate ion. For example, nitric acid, which is a strong acid, and acetic acid, which is a weak acid in aqueous solution, both behave as bases in sulfuric acid. Similarly, phosphoric acid behaves as a base in sulfuric acid. Other compounds that behave as bases in sulfuric acid are amides, esters, ketones, phosphines, urea, formic acid, and oxalic acid. Unlike acetic acid, formic acid and oxalic acid are unstable in sulfuric acid and decompose to give carbon monoxide. A number of examples are known where the organic compound first undergo proteolysis followed by complex reactions. It is found that all species that are basic in nature are also basic in sulfuric acid. Ethers. Ethers are monoprotonated in sulfuric acid. Ether plus acid gives Eth plus HSO4 negative, and the reaction is further followed by solvolysis. Solubilities in sulfuric acid. The dielectric constant of sulfuric acid is greater than that of water. As a result, sulfuric acid should be a better solvent for ionic solutes. However, because of the high degree of hydrogen bonding in sulfuric acid, it is difficult for a solute to dissolve unless the molecular aggregation present in sulfuric acid is disrupted. In such cases, the solute is highly solvated. Solvation occurs only when the solution is ionic or reacts with the solvent to form ions. Solvation also occurs in cases where the solute itself is strongly hydrogen bonded to sulfuric acid molecules. A solute will behave as non-electrolytic in 100% H2SO4 if it is very weakly basic in nature and does not accept proton from sulfuric acid. However, for such a solute to dissolve, it must be capable of forming hydrogen bonds with sulfuric acid. Alkali and alkaline earth metal halides react immediately with 100% sulfuric acid with the evolution of hydrogen chloride in case of metal chlorides of and bromine in case of metal bromides. It is important to note that because of the highly acidic nature of sulfuric acid coupled with its ability to bring about solvolysis, many of the solution process involve the formation of several different ions or molecules from a single solute molecule. Some of the examples are illustrated below with the number mu of ionic or molecular species formed from one solute molecule. The values of mu are determined cryoscopically. Conductances in sulfuric acid. Sulfuric acid is highly viscous and the viscosity of sulfuric acid is 25 times that of water. As a result, the mobility of various cations and anions is 100%. Sulfuric acid should be quite low as compared to that of water. The ionic mobility of Na positive, K positive, Ba double positive and H3O positive in 100% H2SO4 is very small. It is in line with the viscous nature of H2SO4. However, a careful inspection reveals that the mobilities of H3SO4 positive and HSO4 negative are very much higher than those of other ion in 100% H2SO4. In spite of highly viscous nature of 100% H2SO4, it has an appreciable electrical conductance because of the high mobilities of H3 SO4 positive and HSO4 negative ions together with the considerable degree of ionic dissociation of sulfuric acid. The exceptionally high mobility of HSO4 negative can be easily explained on the basis of very low transport number of the cation in solutions of various metal hydrogen sulfates and 100% sulfuric acid. If you recall, transport number measures the relative amounts of current carried by the cation and anion of the given electrolyte. A high T negative value indicates that the anion moves much faster than the cation, hence conducts a large fraction of the total current compared to the counter cation. H3SO4 positive and HSO4 negative ions have mobilities that are greater than any other ions in sulfuric acid. It is also interesting to see that the ions hydronium and hydroxide in aqueous solution have exceptionally high mobility. The mobilities of H3SO4 positive and HSO4 negative ions are unaffected by the high viscosity of 100% H2SO4. This is because the H3SO4 positive and HSO4 negative conduct by a proton transfer mechanism, which is also true for the high mobilities of hydronium and hydroxide ions. In aqueous medium, we can picture water molecules connected by hydrogen bonds in a network. The effective movement of H3O positive ion through the aqueous solution can be imagined by the very minor shift of proton along the chain in the manner indicated by the arrows. There is in fact no mass movement of water molecules involved in the process. It is only the shift of proton that occurs very fast. A similar mechanism can be proposed to account for the mobility of hydroxide ions in water. Similarly to water, the molecules in 100% sulfuric acid are connected through hydrogen bonding in a network. The effective movement of H3SO4 positive and HSO4 negative ions occurs through the proton transfer mechanism. As in the case of water, the mechanism is illustrated below for H3SO4 positive and HSO4 negative ions. Successive transfer of protons along hydrogen bonds result in an effective movement of H3SO4 positive ions through the solution without the need of the actual movement of individual ions. It is because of the high mobilities of H3SO4 positive and HSO4 negative ions. The electrical conductance of various acids and bases in 100% sulfuric acid are determined by the number of H3SO4 positive and HSO4 negative ions per mole of a particular acid or base in sulfuric acid solution. In other words, the measurement of electrical conductances provide valuable information concerning the ionization process for certain electrolytes. In brief, 100% sulfuric acid is a highly acidic medium with high dielectric constant. It has high electrical conductance. It is nearly 25 times more viscous than water. Very few substances dissolve in 100% H2SO4 as non-electrolyte. Most of the substances, especially the organic compounds, behave as bases in sulfuric acid. Many ionic compounds are soluble in sulfuric acid but undergo solvolysis during the solution process. The strongest base available in sulfuric acid is the HSO4 negative ion, and the strongest acid is H3SO4 positive. The neutralization reaction in sulfuric acid system involves the interaction of H3SO4 positive ion and H3SO4 negative ion. Liquid sulfur dioxide as non-aqueous solvent. Sulfur dioxide is a gas at room temperature and atmospheric pressure. It can be easily liquefied and can be maintained in the liquid phase in ordinary Dewar flask. It is used to carry out a number of chemical reactions. It is a non-protonic solvent. Some of the important physical properties of liquid sulfur dioxide are listed here. A close inspection reveals that the dielectric constant of liquid sulfur is low, which makes it an ideal solvent for covalent compounds than for ionic compounds. Bromine, chlorine, iodine, monochloride, thionyl chloride, carbon disulfide, phosphorus trichloride, phosphorus oxychloride are miscible in SO2 in all proportions. With few exceptions, liquid sulfur dioxide is an excellent solvent for a variety of organic solvents. Amines, ethers, alcohols, esters, sulfides, carboxylic acids, and mercaptans are readily soluble. Alkanes have only limited solubility in sulfur dioxide, whereas alkanes and aromatic hydrocarbons have higher solubilities in liquid sulfur dioxide. It is the different solubilities of alkanes and alkenes in liquid sulfur dioxide that is the basis of refining of petroleum. Among ionic compounds, the iodides and thiocyanates are in general most soluble in liquid sulfur dioxide. The solubilities of alkali metal halides in liquid sulfur dioxide decreases in the order iodide ion greater than bromide than chloride. A similar trend is also observed in liquid ammonia. It is important to note that tetramethyl ammonium halide CH3 4NX, where X is equal to Cl, bromine and iodine are freely soluble in liquid sulfur dioxide. The extreme solubility of these compounds is because of the lower lattice energies of these compounds. Autoionization. The electrical conductivity of pure liquid sulfur dioxide can be explained in the terms of self-ionization according to the following equilibrium. The thionyl ion is analogous to the hydronium and ammonium ion, whereas the sulfite ion is analogous to the hydroxide ion and the amide ion in water and ammonia solvent system respectively. Reactions in liquid sulfur dioxide. Reactions occurring in liquid sulfur dioxide can be broadly classified as acid-base reactions, solvolytic reactions, solvation reactions, precipitation reactions, complex formation reactions, redox reactions, reactions with organic compounds, amphoteric behavior.